All right. Hello, everyone. My name is Mauritz from Dissel, and in today's talk, I want to present our latest work in the network inequality group, which is titled hyperFA, a hypergeometric approach to fair rankings with finite candidate pool. So basically, in this presentation, I want to walk you through how to define a fair ranking, so like how we do it, and how the finiteness of the population influences this choice. So let us start with an example. Let's suppose we are organizing a conference and 10 candidates apply. Unfortunately, we have unlimited spots, so we can only select 6 of these candidates. So to do this, we score them based on their CVs and motivation letters, and then we rank them in a decreasing order. And finally, we select the first 6 candidates. Additionally, though, we also have information about the demographics of these individuals. For example, in this case, we could have information about the gender. So we ask ourselves, have we been biased towards the protected group? For example, it could be females. And if yes, how can we measure this and how can we counteract this? So let us, for instance, consider the whole ranking. And in particular, let's look at the proportion of the protected candidates in the top K subsets. For example, on the left, we have 0 protected candidates, so the proportion is going to be 0. Also in the top 2, top 3. Finally, in the top 4, we have 1 protected candidate, so the proportion is going to be 1/4. So the first thing that we can do is plot this line. And ideally, we would like this green line to lie around this 30% dashed line, which represents the total proportion of the protected candidate in the candidate pool. But we also know there are some constraints. First of all, we know that, for example, mathematically, we cannot achieve always the proportion that we desire. For example, in the top 1 subset, the only proportion that we can achieve is either 0 or 1. Also, we need to consider the stochasticity of the selection process. And finally, we also need to consider that this plot is actually bounded in the sense that we have some impossible regions that are proportional that cannot be achieved. In particular, for example, we cannot have 50% of representation in the top 8 because only 3 protected candidates are present in the sample. And also the upper boundary line indicates that we selected all the protected candidates and the lower one that we selected all the non-protected ones. Okay, so let's go back to our fair ranking. Now, to our ranking, so what we would like to achieve is that the pool of the selected candidates more or less mirrors the pool of the distribution of the protected candidates in the overall, the whole of the ranking. So basically, we want to achieve demographic parity. In order to decide how to do this, we would like to compare our ranking to other rankings that are generated in a fair manner. And fair in the sense that those are rankings that are kind of independent from the protected attribute. So in which we sample where the membership to the protected or non-protected group at random. So in particular, we consider this as a norm problem. And first of all, the first model we consider is the finite, what we call the finite binomial sampling, which was introduced by Young and Stojanovic. And the idea is that at each draw, we select a protected individual with a fixed probability f until candidates from both groups are present. What we introduce instead is the hypergeometric sampling. So basically, in this case, at each draw, we select a protected candidate with a probability that is equal to the proportion of the protected group inside of the individuals that are still present in the urn. So for an example, if we start with 30% of probability for both cases in the beginning, the difference is that for the hypergeometric, this probability will change depending on who has been selected throughout the process. So in the paper, what we show are, first of all, some key properties that differentiate these two models. First of all, we know that the hypergeometric model has tighter confidence intervals, especially when k grows large. So in the plots on the right, what we show is the 90% confidence interval, two-sided, for both models. And we can see that for the hypergeometric case, the confidence intervals are more tighter towards the mean, and also this means that it avoids the boundary region. So we avoid having only one demographic in the bottom of the ranking. This also means that it leads to more restrictive tests when k is large, so we demand for higher fairness. The hypergeometric model is also more accurate when the number of protected individuals is particularly small. For instance, if we have only 1 protected candidate and we sample in the first 5 draws only non-protected ones, now the probability of sampling a protected individual doubles, while for the binomial model it will stay the same. And finally, we formally show that the hypergeometric model considers also fairness in the bottom positions. In particular, we show that the distribution in the hypergeometric case mirrors the one for the distribution in the hypergeometric case for the bottom position. So instead of looking at the top, now we look at the bottom. Mirrors the one for the hypergeometric case because of the symmetry of the distribution. For the binomial, it doesn't, and let's say it shows a different distribution. So if we would assume that the finite binomial is the fair distribution, this wouldn't be the case. But what if, for example, we would like to have something beyond demographic parity? So, for example, we would like maybe to enhance the participation of women or of other groups. So basically, we would like to set some desired proportion, some quota, that is different from demographic parity. So for the finite binomials sampling model, this is quite straightforward. We simply choose f equal to the proportion I want to achieve, and this is done. While for the hypergeometric case, this is not possible because it only depends on the proportion that is present in the urn. So in order to do this for the hypergeometric case, we need to consider the non-central hypergeometric distribution. So in this case, we weight the protected candidate more or less depending on the case, in this case more, so the probability of selecting a protected individual in the first row is equal to the desired proportion. So in this case, again, we start with the same probabilities in the beginning, and for the hypergeometric, this distribution will change depending on who remain in the urn. So what we show also in the paper is that these two models have some underlying differences in the interpretation of fairness in these affirmative action cases. For the finite binomial, what we observe is that the model will try to achieve the desired proportion throughout the ranking until it will hit, let's say, the boundary region, and then only one demographic will be present in the ranking in the bottom positions. While for the hypergeometric case, we see that it satisfies the quota for the top positions, while it will slowly converge to demographic parity as more candidates are sampled. This means that, first of all, we avoid the boundary regions, so we kind of fare towards the bottom positions. If the quota is set lower than the goal representation, we avoid the underrepresentation of the protected group. And finally, if instead the quota is set higher, we avoid reverse discrimination. So we argue that this kind of makes it easier for policymakers to argue why this should be implemented. And finally, I just want to show some brief applications that we do with our package. So this is a ranking from a university in South America based on the GPA of the students, and the protected group are low socioeconomic status individuals. And first of all, what we can do is that we can test the proportion for the top K to see whether it's balanced or not. We do this through like a hypergeometric test. We can test the first K prefixes from 0J to K together, like the fairness definition that has been defined in the paper by Zalik et al. We can re-rank the ranking in case it doesn't satisfy the fairness criteria. We can change the type of test. So in all these cases, usually we test for underrepresentation, like we could also do two-sided tests or test for overrepresentation of the group. And finally, we can add weights as we just saw. Okay, this was all. Thank you all very much for your attention. I also want to thank my collaborators.